So now we have, if you look at these terms in the Euler equation, you see that these terms are both gradients of scalar quantities. And what we've just done down here is express the pressure term also as a gradient of xj, this third term up here. So we can express these whole three terms as the gradient of one scalar quantity. So let me write that out. Let's rewrite Euler. We still have dui dt. And then let's take this second term over onto the other side. So that becomes positive. I'm turning everything positive here. And then here we get a term d by dxi that has three scalar components, namely gz plus, and now we have this pressure term, plus a half q squared. And essentially, these are all pressures of some form or other. And they carry the following names. Gz is known as the body force pressure. This term is the static pressure. And this term is the dynamic pressure. And the whole three terms together are known as the Bernoulli function, B, which is also sometimes known as stagnation pressure. And so we can rewrite this in vector form. And actually, let me just copy that once more. So in vector form, this is just B. So then we have du dt plus the gradient of the Bernoulli function is u cross omega. So for example, let's consider now a steady flow. That means du dt is 0. So this term goes to 0, and we're just left with the gradient of B is u cross omega. That means that the left-hand side here, that is a vector that is perpendicular to the constant B surface. Vector perpendicular. Now, the streamlines are determined by the direction of u. So the streamlines are tangent to u, and the vortex lines are tangent to omega. So a vector that is tangent to u and tangent to omega, if we take the cross product of those two, we must get a vector on the right hand side that is perpendicular to the streamlines and the vortex lines. That means that the constant B surface is parallel to the streamlines and the vortex lines. Yeah, i.e., along the streamlines and along the vortex lines, B is constant, and that is the Bernoulli equation. So graphically, if I have streamlines going in one direction and vortex lines going in the other, and it doesn't really matter what the angle is between those, right? But what is always the case then is that this surface here, which contains vortex lines and streamlines, has a constant b value. And this contains the streamlines and vortex lines of your flow. So we can write the Bernoulli equation as follows. B is equal to a half q squared plus p0 to p 1 over rho dp dash plus gz. And that is constant along streamlines and vortex lines. And this thing is what we call the Bernoulli equation. In what sense it's useful, we will look at that with a couple of examples later. So it holds for barotropic, inviscid, steady flow. One final thing, if omega is 0, i.e. if there is no vorticity, meaning irrotational flow, here one more condition that we can apply. For irrotational flow, we find that grad B has to be 0. That means this quantity, a half q squared plus p0, so this stagnation pressure in that case is constant everywhere.